Okay, today we're going to talk about shocks. So picking up what we started last time. So last time we looked at a bunch of pictures of shocks. Now we're going to do a bunch of math. So let us make a quick outline. So I'm going to start with the method of characteristics and steepening of shocks into shock waves. So why does a shock form in the first place? We're also going to talk briefly about finite time singularity. And this is cool because this shows, so Euler or Navier-Stokes has two components. One that is a diffusive component that I know is stable, and we understand diffusion really well. And we understand that diffusion is stable. And one that we know blows up. So today I'm going to show you how that one term blows up and how you can get infinite velocity in a finite amount of time. Infinite velocity in an infinite amount of time isn't very interesting, but infinite velocity in a finite amount of time is very interesting. That means I can make something go weird while I'm watching. So we'll talk about those things. And then we'll talk about the Rankine-Hugoniot relations and shocks, and then there's something else. Stevening, Burgers, Rankine-Hugoniot. And then if I've got, depending on how long that takes, I will talk about dimensional analysis, which leads us into the Sedov-Taylor. This is the Taylor. This is the blast wave solution. And then if there's still time, I'll talk about Laval. Which is how you make a supersonic flow in the first place in the lab. The Laval nozzle is really fun because it's a really simple device, but it is really counterintuitive. Okay, so first thing I'm going to start with is scalar advection. Okay, so we remember that Navier-Stokes says d by dt of v plus v dot grad v equals -1 over rho grad p plus nu del squared v. So this is Navier-Stokes. Now, I'm just going to think about this first term for a second, the left-hand side. So let's say now we're going to have something that looks like the left-hand side. We're going to forget about pressure. We're going to forget about viscosity for a second. So forget about those guys. Let's just think about the left-hand side. If I say that if C is a constant and I have some quantity Q, Q could be anything. Q could be the density. It could be the concentration of a contaminant in a river. It could be velocity. It'll be velocity in a second in certain scenarios. If I have something where the speed of propagation doesn't depend on anything else, then I can say d by dt of q plus c d by dx of q equals 0. So this is the scalar advection equation, and it looks a lot like the left-hand side of Navier-Stokes on purpose. But what does this do? So I'm going to tell you, and then I'm going to show you. What this does is if I have some initial perturbation, this perturbation just travels to the right at some velocity c. So I start off with some initial condition, and it just moves. So this is just advection. It's just moving stuff around with a fluid. So how can we see that that's what this equation is telling us, we're going to use the method of characteristics, which is a complicated name for just saying I'm going to do chain rule backwards. So this is my constituent equation. I'm going to undo chain rule, and remember how we got this in the first place was just d by dt. It's just the full derivative. So this is just dq by dt equals 0. And dx by dt equals c. Does that make sense? So that's all. These two things are saying the same thing. This is just chain ruling this guy, knowing that this is true. So maybe this is how we got the first equation. Maybe it's not. Maybe we go backwards. This is the equation that I'm starting with, and I can see that this is true, and I can see that this is true. Now these are both ordinary differential equations. Let me pause for a moment while you sit down, and then I'm going to back up because you just missed the setup. So I'm just going to vamp for like 30 seconds while you get ready. Maybe I'll have a sip of cup. So the basic idea now is I have some flow, some system where I have some concentration of a contaminant or a density or something else that just gets pushed around with a fluid. That quantity follows the scalar advection equation, which is this. So dq dt plus c dq dx, where q is, say, my concentration of pollution in my region. So we just undo this in chain rule, and we get the full derivative of q with time is equal to 0, and the full derivative of x with time is equal to c. So this is now two ordinary differential equations that I can solve, right? This is the full time derivative, so I can just integrate. I integrate with time, and I'm left with q of x and t equals, well, I just integrate 0. I just get my integration constant. So I just integrate, I get just my integration constant. But my integration constant is just my initial conditions. So this is q of x naught t naught. That make sense? So this tells me that my flow always kind of looks like my initial conditions, just because I just integrated that. And this one says that x equals ct plus x naught. Just once again integrating this and then applying the initial condition that I know, that is x naught. So now I can solve a little bit, and I can say that x naught equals x minus ct. And I can take this equation and I can say that q of x minus ct equals q of x naught t naught. So what this says is that my solution at some time t is just my initial conditions advanced by some velocity. Can everybody see that? All right. Does that make sense? So we've done two things. So the first thing we did was method of characteristics, which is just chain rule going backwards. So we just took this equation, collapsed it with chain rule, and we get this ordinary differential equation that I know how to solve. And I solve it, and I just get that q is equal to my initial conditions. I solve my x, and I'm left with x is equal to ct, or x naught is equal to x minus ct. And I plug that into here, and I get that whatever my solution is just my initial conditions shifted by a certain amount of time. Yeah.
So is c just some constant that relates to the system?
That's just the velocity of things moving around, whatever that velocity happens to be. So Jesus gave you some system that has some velocity.
Okay.
So this is relatively simple to solve. Relatively simple. I mean, until you've done it once, it's a headache. So let's now talk about what the big difference is between this and the left-hand side of Navier-Stokes. The big difference between the left-hand side of Navier-Stokes and this is this guy is not a constant, this is now the velocity itself. So that's easy enough. Let's talk about that. So we'll just do this again. I don't actually need to erase all this because it's, I'm going to back up a little bit. So now, let's just take just the left-hand side of this. So I'm going to write some stuff down here. d by dt of q plus c dx dq dx equals 0. This is scalar advection, where c equals constant. And then this one, d by dt of v plus v dx dv dx. This is called Verger's equation. And it's just the left-hand side of Navier-Stokes equation. Here, v is not a constant. Here now v is a variable and it's going to change. V is the same as this v, because that's what we've got here. So now we're saying that the velocity that this signal propagates with is also the velocity. So I'm going to start with a simple cartoon example. If my velocity goes like this is x and this is t, if I start off with a high velocity here and a low velocity here, what's going to happen? This material here is going to run into this material here. And it's going to get steeper and steeper and steeper until it's just a plow, because the material, a bit of gas can't move through another bit of gas. I mean, okay, it can, but that's high Reynolds flow, and that's not where we're at yet. So in this scenario, gas can't move through other bits of gas, they just pile up. So if I start with low velocity on one side and high velocity behind it, then it's going to pile up and make a shock. Does that make sense? So I'll show you that in a second, or I'll show you that now. So let's forget about that for a second. I'll show you how this math works, and you'll see the infinity. So I start with d by dt of v plus v d by dx of v equals 0. So method of characteristics says I just undo this with chain rule, and I get the full derivative of v equals 0. And I in undoing chain rule, I have to talk about what this is. So this is going to be d by dx of t, or d by dt of x is v. Once again, I can solve these equations. These are simple, ordinary differential equations. This is just the derivative of something is 0, so that thing is a constant. So we can say that v of x and t is equal to v of x naught t naught. So this is my initial condition, and this is my condition later. So those two things are related. And here we can say that x is simply vt plus x naught. X naught being my initial condition. So this is the same set of equations that we had before, but now let's start with initial condition. Let's give us an initial condition. V of x naught t naught equals some number a times x naught plus b. Let's make this negative so that it's going down, so that it's getting faster. All we're going to do is take these two statements and plug them into here. So we just plug it. So once again, x naught equals x minus vt. So I plug that into here, and I'm left with v equals minus a times x minus vt plus b. So just expand this out, and I'm left with ax minus ax plus avt plus b. Put this to the other side, I'm left with v times 1 minus at equals v minus ax. So v equals v minus ax over 1 minus a times t. So what does this do as t approaches 1 over a? What's that?
Blows up.
It blows up to infinity, right? Because it goes to 1 over 0. So this method of characteristics, the book's description of it is kind of terrible. Because method of characteristics is actually really simple. It's just pretend the chain rule works everywhere, which it does. Undo chain rule, turn everything into an ODE if you can, and then integrate. And what we see is that for the right initial conditions, so this is always general. This stuff is always true. This is a specific example of how the left-hand side of Navier-Stokes equation can blow up given the right initial conditions. Now when you add the other side, then it stops blowing up, but there's still an open question. Does there exist any initial conditions that will make this go to infinity in a finite time? This is called the finite time singularity problem, and if you can solve it, you'll be super famous. Yeah.
Why is that important to know?
The solution space to Navier-Stokes?
No, like in this case, like why is it important? Like at what point is it gonna like blow up?
Well, because that's when something bad is happening in your system. So that tends to be when your approximation is breaking down. Ultimately, if you get infinities out of the math, that means your approximation is wrong. Usually, if you get infinities in the math when you're trying to solve gravitational collapse, you get a black hole. So infinities tend to mean that something weird is happening and you need to pay attention there. So here, I have this pile up and it makes an infinite velocity because so my initial velocity looks like this, and this stuff is moving faster than this stuff, so it just pancakes into this stuff and the velocity goes crazy. That is without pressure and without viscosity. When you add pressure and viscosity, the problem gets a lot harder. But this is useful because we can see just what this term wants to do. What this term wants to do is become singular. Okay, so now that we know that Navier-Stokes wants to make things do this, let's skip a step and assume that this has happened and we have a discontinuity. So if we have a discontinuity in, I have rho 1, V1, and P1 on this side, and rho 2, V2, and P2 on this side, I have a discontinuity in my fluid quantities. So when I have something like div rho V equals some stuff, what's problematic about that? This is a derivative, and this is a step function, and you can't take the derivative of a step function. There's no, the derivative of this is not defined at this point, right? And I can show you why, but that's kind of boring. But basically, there's no way to define an actual derivative at this point. It could be anything, it's ill-defined. So what does that mean for Navier-Stokes? It means it's not defined when I have a discontinuity, but I can integrate it. So I can still integrate. You can integrate anything. You can't differentiate everything. So you can differentiate some things. Almost everything is integrable, unless it blows up to infinity. So what are we going to do? We're going to do two things. So we're going to say first, I'm going to be moving in the frame of the shock. So I'm going to sit here, moving along with the shock. And because of that, I'm going to assume that we're in steady state. So let me write up the rest of the constituent equations that I don't need over here. So we also need d by dt of rho plus div rho v equals 0. And we also need the energy equation, because we're going to need that. So and that says that d by dt of rho e plus 1/2 rho v squared. This is the total energy. Rho e is the internal energy. And 1/2 rho v squared is the kinetic energy. So this is the total energy that the gas can experience. And I'm just going to write this down. It's a homework assignment. This is minus div of this expression, rho v squared, 1/2 v plus w, where w is the enthalpy. Yeah, that's right. And then there's a conduction term, but I don't really care about the conduction term right now. So we're just talking about things exploding, and generally when something's blowing up, there's not enough time for thermal conduction. So this is not an equation that I've written up for you guys yet, but you get it by taking the internal energy equation, which I did write down, and the other two equations, and massaging them to get them into the form. So you start by saying, I want to know the total energy, because I know that's what's going to be conserved. So I just take this, I chain rule it out, and I replace all of my time derivatives with the space derivative equivalent, and I'm left with it. You just got to integrate by parts a couple of times. It's not really that bad. That being said, when you get to that homework problem, you're going to kind of tear your hair out because it is a lot of bookkeeping. But it's a valuable exercise to go through in making these equations. So these are both, oh, and I need to rewrite Navier-Stokes as the conservative equation. D by dt of rho v equals minus div rho v plus p. Well, now I'm being a little bit sloppy with my notation, but this is what you get. So you get, this is again the velocity tensor, but really just think about this as vi, vj, and I have a j on this derivative and an I on this vector. So this is the Euler's equation written in a conservative form. So now we have an equation for the momentum, which this is also a homework problem. So you get this by just taking this and integrate by parts once. So the reason that I want to write these down in conservative form is each one of these is in a form of d by dt of q equals minus div some flux. Does that make sense? The reason that I want to write these down is because now the right-hand side is a full derivative. So that I can just, now this is a differential equation that I can solve. I can just integrate. If I have things like this 1 over rho grad p hanging around, this is not a full derivative, so I can't just integrate it because it's rho times grad p. But if it was just grad p, I could integrate it. This is now, all of these are now div f, so I can just integrate. So for each one of my 3 constituent equations, we have continuity, internal energy, and the momentum equation, I'm going to do the following things. So the first thing I'm going to do is say that d by dt of whatever is 0. We're moving along with the shock, so we don't experience anything locally changing with respect to time. So the time derivative holding everything else fixed is 0 because I'm traveling with this shock. I'm just seeing stuff coming in and stuff going out. And then the second thing we're going to do is that if we're going to integrate div f to just get f2 minus f1 equals 0. Where f2 and f1 are the 2 different sides of my shock. So like up here. So here I've got an f1 on this side and an f2 on this side. Does that make sense so far, what I'm going to do, or how I'm going to get there? So the first one, continuity, is straightforward. So continuity, we say d by dt, no, we're setting the d by dt term to 0, so we're left with div rho v equals 0. I integrate that, and I'm left with rho 1 v1 equals rho 2 v2. Does that make sense? This should be super clear now. And if it's not, stop me and I'll go back over it. So we just integrate this rho v term to get rho 1 v1 equals rho 2 v2. So by the fact that mass is conserved, it doesn't matter how I've set this scenario up. It doesn't matter what I use to blow this thing up to make this shock, to drive this very fast wind. It doesn't matter this is going to be true because mass is conserved. So now let's look at the momentum equation. So the left-hand side goes away, and we're left with just the right-hand side, and we've got just rho VV times P, and we're in just one dimension, so we only have to deal with the x derivative in the x direction. Everything else is 0. So this just becomes d by dx of rho Vx Vx plus P. So I'm just left with then rho V squared, rho 1 V1 squared plus P1 equals rho 2 V2 squared plus P2. Does everybody see that? Does that make sense, how I got to here from here? Does everybody understand where I got this from too? Or at least basically? Yeah.
Just to check, that partial t rho vi is 0 because of the way the frame is defined.
That's right. So we set this part to 0 because I'm moving along with the shock. So let's set that to 0. So we've boosted that away. And then we have the third equation, and I have a rho and an epsilon. And there's in W, this is epsilon plus P over rho. There are several equations. And then you have the ideal gas law. And as I said several times before, watching me do algebra is boring. So I'm going to skip the algebra and leave it once again for a homework. Homework 3 is going to be long. Oh, administrative stuff. I went through and touched up the calendar online. So the calendar now, basically, I may shift things backwards in time a little bit, but nothing's going to be coming forwards in time. That being said, I also didn't want to introduce 2 new homework. When I got there, I was like, oh crap, I'm missing a homework step. I'm just going to make 3 long. So homework 3 and probably homework 4 are going to be kind of long, but make sure you leave yourself some space for those. They're not going to be horribly painful. It's just there's a lot to cover because there's a lot of fun things. So doing this next step is going to be a homework assignment because watching me do it isn't very instructive, but seeing the result is instructive. So here we're just left with, after a bit of algebra, 1/2 V1 squared plus gamma P1 over gamma minus 1 rho 1 equals 1/2 V2 squared plus gamma P2 over gamma minus 1 rho 2. So this is the way that the internal energies are related. And you can see this is the internal energy per unit mass, V squared. So rho V squared is the kinetic energy. The kinetic energy per unit mass is just V squared. This is the internal energy per unit mass. Gamma P1 over gamma minus 1 is the internal energy, and rho 1 is the mass. So this is just a statement of energy conservation. And this one is just a statement of momentum conservation. Now, you can see that. It was mass conservation, but now it's momentum conservation. And the other thing you can think about is this term here, rho V squared. It looks a lot like 1/2 rho V squared, but it's a very different quantity. This isn't the kinetic energy. This is called the ram pressure. So if you have a flow coming at your face with some velocity V, the pressure you feel from the flow is rho V squared. So you feel an additional pressure from the wind that is this large, in addition to P1. So we can take these a step further and we can talk about some things. So when I have a shock, I can also talk about what the density jump is across that shock. So you just take these 2 equations and you solve for rho 2 over rho 1, and you're left with gamma plus 1 times the Mach number squared over 2 plus gamma minus 1 times the Mach number squared. So this tells you how much denser it gets. This is kind of useful. Oh, and we've defined the Mach number here. The Mach number is the velocity divided by the speed of sound. which is a quantity that shows up a lot and is going to show up a lot when we get, or it's going to show up again when we get to Laval nozzles. The Mach number tells you how fast the flow is relative to the sound speed. So it becomes an important quantity. So from this, if I have the Mach number goes to infinity, we can see that the density jump, board space, let's start up here. Let's eat into the previous statements. So as the Mach number goes to infinity, rho 2 over rho 1 equals this over this. This 2 becomes inconsequential, and then the m's cancel out, and you're left with gamma plus 1 over gamma minus 1, which if you plug in 5/3 for this, you get 4. So in one dimension, regardless of how fast your flow is, the density is going to get bigger by a factor of 4. And if gamma is 1.4, this is good for air, then you get 2.4 over 0.4 is, somebody do that math in their head, 6. So this gives you a factor of 6. So air, you can get more compressible. Air can compress more than monatomic hydrogen. Why does air have a gamma of 1.4? So this is, you may have seen this, you may not, but gamma is the number of degrees of freedom plus 2 over the number of degrees of freedom. So if you have a monatomic gas, then the number of degrees of freedom is 3, because it has three position variables. If I have a diatomic gas, then the number of degrees of freedom is 5, because I have 3 positions that it could be in, and then it has 2 rotational components. So for a diatomic gas, you get 7/5, which is 1.4.
Could you just really quickly tell what V and W is in the energy freedom?
Here,
Yeah.
V is velocity. V is always velocity. I'm never going to use V for anything else. Unless it's volume, in which case I try to make it really obviously big, but it's never volume. And W is the enthalpy. And the enthalpy is the internal energy plus P over rho, which is the cost. It's kind of like a work function. So P over rho is kind of like P times V, which is like the result of integrating P dV-ish. Okay, so there's going to be some homework on that. And so you can go down this rabbit hole further and talk about the temperature jump and talk about the velocity jump. One of the intriguing things about this wind tunnel that I've started working with, they can make it go Mach 5, but they can't make it go faster than that, because as the gas comes out of the nozzle, the temperature drops below the liquefaction temperature of air. So that's problematic, because then the air liquefies on the way out. And then you have droplets of water moving at Mach 5. So anyway, is there anything else that I have to say about shocks? About shocks right here? I think that's all I got. So let's talk about dimensional analysis. Yeah.
So just to get my head around what exactly the one side and the two side is. So is the one side like the shock front, and the two side is just the stuff you're pushing out of the way?
It's whatever. So if my shock is flowing in this direction, then V1 is going to be the gas speed. The shock velocity will have its own velocity, which you can solve for, which I did, but I didn't have as part of today's lecture. Maybe I should do that. I don't have it pulled up in a way that makes sense. But so the front is moving at a certain velocity. The gas on either side is going to be moving at their own relative velocities relative to that front. So if, for instance, I have an explosion and I have static air here, V2 is going to be 0. V1 is going to be the velocity of the gas post the shock. The shock is actually piling stuff up as it goes, so it's moving faster than what the gas is doing because it's piling stuff up. So that pile up goes faster than what the gas is doing. And then rho 2 is the ambient temperature, and rho 1 is the temperature behind the shock, the density behind the shock. But because this is an integral relationship over these differential equations, as long as throwing out the left-hand side is reasonable and it's basically one-dimensional, this is always true. It doesn't have to be a discontinuity. This is true if this is some crazy nonsense that I don't understand. I have a point here and a point here, and because these are integral relations, as long as I'm moving with the flow, that's always going to be true. So these are jump conditions, they're shock jump conditions, but they're really a statement about any 2 points that are moving along with the flow. Okay, yeah.
For like stuff orbiting Earth in space, like they're obviously moving really fast, like at some mark. So they're not, are they breaking without barrier, or is it like a time, like is there like a time difference that needs to, like this something needs to move really quickly in a certain amount of time so that it creates a shock wave, or like are they not creating?
There's a shock in front of there has to be a bow shock in front of the space station, because the space station is moving at 17,000 miles an hour, and the sound speed up there is not 17,000 miles an hour, it's a lot lower. So so the sound speed goes like the square root of the temperature, and the temperature up there is pretty low, so the sound speed is pretty low. But the mass of air that you pile up in front of the space station isn't that much to really damage the space station. It is enough to slow it down though. So periodically they need rockets to push it back up because of the drag, and the drag is a shock drag. But that's a good question. Okay, dimensional analysis. So this is something that increases, my amazement at this increases the more I do physics, is that as long as you have the units right, you're like 80% of the way there. So as long as you can get the ballpark, you're mostly done. And then the rest of it is the other 5% of the answer that is probably what you're looking for. But just by asking what are the dimensions of the problem, you can do an enormous amount. So let's say I have an explosion that starts off with some energy, E, and it's moving into gas that has some density, rho, and it's evolving with time. As long as everything else is basically static, these are the only things that it can really depend on, is the ambient gas and the energy of the explosion. So what we want to do is we want to get an estimate of the radius of the explosion, just assuming what we know about the energy of the explosion and the density that it's running into. So what I'm going to do is I'm going to say that E to the A times rho to the B times T to the C equals a length, centimeters. This is a super general process that you can do kind of all the time. If I have some combination of things and I want to smash them together in some way that gets me some other combination of things, I can just do it this way. So I write down the things that I want. Now I didn't think about, like, I know that's just going to be multiplicative, so I'm just multiplying them all together. And if I have to be dividing, that'll show up as one of these exponents will be negative. So, oh, I need a quick aside. How many of you guys are comfortable with the concept of an erg? How many of you really have no idea what an erg is? How many of you kind of heard about an erg but aren't really very comfortable with it? All right. So an erg is just a joule, but it's only 10 to the minus 4 of a joule. Maybe it's 7.
I think it's 4.
Uh,
Oh
yeah.
no, maybe it's 7, because I think 4 is dyne.
Yeah, so a dyne, so an erg is an energy. A dyne is a force. So I will get to plasma physics and I will talk about why astronomers are stuck on using CGS. The upshot is because when they developed MKS SI in the 50s and 60s, they did a crappy job because they included the ampere as a new fundamental unit, which is completely unnecessary, and broke the symmetry between the electric and magnetic fields. Electric fields and magnetic fields should have the same units, but they don't in SI. But they should, because you can fold them into each other. But if you're never folding them into each other, if you're not doing anything relativistically, you don't care. So the engineers don't care that if E and B don't have the same units, but I do. So anyway, so the erg is the unit of energy in CGS, and the dyne is the unit of force in CGS. So you can sort out what they are. An erg, it's energy. It's going to be a mass times a velocity squared. So this is going to be a centimeter. This is going to be a gram centimeter per second squared. And a dyne, which we use less often, is a gram centimeter per second squared. An erg is about an ant push-up. An ant doing a push-up is an erg. So an ant weighs about a gram. Okay, maybe you need one of those big palmetto bugs because they're more like a centimeter. But an ant doing a push-up is about an erg. 10 to the 51 ergs is a supernova explosion. Why use ergs for such a huge thing? It doesn't matter. If I use joules, it would be 10 to the 44 ergs, and that's still a stupid huge number, so we'll just keep using ergs. So anyway, so throughout the book, ergs show up. And I'm going to continue to use ergs because I'm an astronomer, and that's what I'm used to. So we're going to do everything in CGS, and we can do this in MKS too, which works out just fine. So E is an energy, so this is going to be a centimeter to the A, a gram to the A, a centimeter to the A, to the 2A, divided by seconds to the 2A. So I'm just raising energy to the A, just plugging in what the constituent units are. And then density is going to be a gram to the B times centimeters to the minus 3B. And then time is seconds to the C, and this is got to equal centimeters. So what I've written down is 3 equations. Those 3 equations are all in the exponents. So now let's think about making the exponents make sense, because that's what's got to fit. So on the left-hand side, I've got gram to the A, gram to the B. And since grams are linearly independent from centimeters, this is a separate equation, right? The grams all have to do something. So this has to equal grams to the 0, because I got no grams over here, right? So what can we say about A and B? Let's solve for B. B equals what? Negative 8. This is just a little bit of algebra. So now, let's look at the seconds. So seconds to the minus 2A, seconds to the C equals seconds to the 0. So C equals minus A over 2. Oh, no, plus. No, C equals 2A. Duh. Because I can do math. C equals 2A. And then let's look at the centimeters. I got centimeters to the 2A, centimeters to the minus 3B equals centimeters. And I know that B equals minus A. So I get 5A equals 1, so A equals 1/5. So now let's plug all this in together. And I'm left with energy to the 1/5 times density to the B, which is minus 1/5, times time to the C, which is 2/5, equals lambda. So let's simplify this. So this is E over ET squared over rho to the 1/5 equals lambda. Make sense? So all I did was write down what the units are that I want. So this is the units that I have, and this is the units that I want. And we just do this algebra stunt in the exponents to get all the units to work out. So my result is ET squared over rho to the 1/5. So this is useful. I can solve, and it works really well. So one of the things that you can do is determine how energetic a supernova is based on how far it moves. So if you plot log of the size, if you plot the log of the size versus time, you'll get a straight line. And the slope of that straight line is going to be the log of E over rho times some number, which is 2/5. So you can get the internal energy of the explosion just from the dimensional analysis. And that's, the book goes through, then takes this to some deeper levels, which is intriguing, but is kind of unnecessary because it's an approximation. So the approximation can be not taken too seriously and still be useful.
Dr. Kamal,
Yeah.
could you just say what that says, like the grade? Like the gradient of the.
Where?
The gradient of the line that you just.
Oh, here. This is going to go like 2/5 times the log of the energy over the density. So it's just going to be, if I'm just looking at the log of this, then and solving for t, then the slope of that line is just going to be everything else that's in front of the t. That's fun. I think there's a homework problem that involves this, but I can't remember. Does anybody have any questions on this? Basically makes sense. So the dimensional analysis stunt is really, I think, half of the fun for this problem because it works so well. Yeah.
Could you explain what lambda is over here?
Oh yeah, lambda is the size of the front. Sorry, I changed variables on you. Lambda is the size of the front. So, and it's expanding at some size at some time t. Yeah. Okay.
Is E supposed to be like the energy at the initial?
Yeah, that's the initial energy of the explosion. Yeah, and so why, you may notice that I didn't have a pressure in there. So one of the assumptions about this is that pressure doesn't matter because it's a shock. So it's a spherical shock wave and not a pressure wave. If it were launching sound waves, then the pressure would matter. But the velocity that we get is so much higher than the sound speed that we can ignore the pressure in the problem. Oh, cool. I'm on the valve nozzles. That is everything I expected to get done today. Sometimes things go faster than I want them to. So, the last thing I'm going to talk about today is this cool thing of a valve nozzle. And the book does not really, like, he talks about them, but he doesn't talk about how cool they are. And then he goes on and talks about spherical accretion, which is intriguing, but is in the modern era of we can do everything with computers now, these spherical models are useful for intuition, but taking them too seriously gets you into trouble. So what I'm going to do now is this Laval nozzle thing. So let us start off with one-dimensional flow. And let's say we're in a pipe. The pipe has some cross-sectional area A. So as you go down the pipe, the cross-sectional area A can change. So if I'm just pushing air through this pipe at some constant rate, then continuity says that d by dt of rho plus div rho v equals 0. So if I'm in a steady state, so that I'm set things up so it's just smoothly flowing through, we can send the time derivative, holding everything else fixed, to 0. And we're just left with div rho v. And we can integrate that, because now I've got div rho v equals 0. So now I have a full derivative here, so I can integrate it. So this, I integrate that, and I get the surface integral of rho v, which is just rho v at a2 minus a1. So where this is going to be a2, and this is a1. Because I know the velocity through, so when I do this integral, this is a volume integral, so it turns into a surface integral over all of the surface. But I know that I only need to deal with the surface on this side and this side, because the surface coming out the wall, the velocity is 0. So the velocity can't go out the wall, it can only go out the front and the back. So I can say that, so rho v a, the surface area, so the continuity equation turns into simply rho 1 v1 a1 equals rho 2 v2 a2. Is everybody all right with that? At least for the most part? So A is my surface area term, and I just have 2 of them, because the other surface area terms go away. So continuity tells us, I'm going to erase all that. Continuity tells me that rho v a is a constant. So now I'm going to take the derivative with respect to x of rho VA, and then I'm going to divide by rho VA. So for each term, I'm going to get 3 terms from the product rule. Oh, that should be a dx. I'm going to get 3 terms from the product rule. It's going to be rho V dA dx plus rho A dV dx plus VA d rho dx. And then I divide by rho VA, and this equals 0. I divide it by rho VA, and I'm left, for each term, I'm just left with whatever thing is inside the derivative. So this is 1 over A dxa plus 1 over rho dx rho plus 1 over V dx V. Or, what I'm going to write up here, because I'm going to want it, d by dx of the log of the velocity plus d by dx of the log of rho plus d by dx of the log of A equals 0. So this is 1 over A times d by dx of A. That's just the derivative of the log of A. Does that make sense to everybody? So this is what I get out of the continuity equation. And I like this, I like writing it this way because log is a monotonically increasing function with the thing that it's on the inside. So if rho is increasing, so is log. So this just lets me see that this is, yeah, so actually, I want to talk about that for a second. Let me write it down again. So d by dx of the log of v plus d by dx of the log of rho plus d by dx of the log of a equals 0. And this is really an acceleration equation. So this is saying that as I'm going down the pipe, these three things have to be related in concert with each other. So if the area decreases, then this term will be negative. That means the combination of these two terms has to be positive. So that means it's either going to get denser or it's going to get faster, or both. Or if the sign is wrong, these can go the opposite direction. So depending on how these guys are related, let's talk about how these guys are related. Let's talk about Navier-Stokes again. So we start with d by dt of v plus v dot grad v equals minus c squared over rho grad rho. Let's call that dx rho. So this is just that again with the viscosity thrown away. That term we're throwing out, so that the only thing we're left with is v dot grad rho and this. So what this says is v dx v equals minus c squared over rho dx rho. So we can move the c squared over here, and this becomes v over c squared. And then I can plug this into here. So now I'm left with v over c squared times dx log v plus, oh, sorry, I need to write this, sorry. I like to think about it this way better, but it's easier to do the algebra with this. So this is 1 over v dx v plus 1 over rho dx rho plus 1 over a dx a equals 0. So this term is this guy, so this just becomes v over c squared dx v. So then I can combine these two terms, and I'm left with 1 over v plus v over c squared d by dx of v. And I could just factor out a 1 over v, and so this whole equation, this becomes, oh, I dropped a minus sign here. There's a minus sign there. Minus sign there. So this is a minus right here. I factor out a v, and this becomes 1 minus the Mach number squared times 1 over v times dx v, where the Mach number is just the velocity in certain units. So my continuity now becomes 1 minus the Mach number squared times 1 over v dx of v plus equals minus 1 over a dx a. So what this says is that as I'm going down my pipe, if my area gets smaller, then this term is positive. And this term has to be positive. But if the Mach number is large, then this bit is going to be negative, and so the velocity has to decelerate. If the Mach number is small, then it will accelerate. So I have several possible phenomena that can happen here. So if my flow gets narrower, so d by dx of log a is negative, then if the Mach number is bigger than 1, let's start with subsonic. If the Mach number is smaller than 1, this is what you get used. This is what you're intuitively used to. So if I have a pipe, so did you ever squirt your water with a water hose when you were trying to do yard work when you were a kid? So if you take a garden hose, you put your thumb over the top, just partially, the water comes out faster. That's because of this. It's because you're restricting you're restricting A, so dA dx has a very sharp negative sign, and so dV dx has to increase. So if you think about, I'm piling things in here at a certain rate, they have to come out here, but because the area is smaller, they have to come out here faster. Right? That makes, yeah.
But there is some factor of the ability to keep pushing that water. It gets harder to push, doesn't it, or no?
Yes.
Okay.
Yes. So it gets harder to push until you get to the sound speed, which I don't think you can do with your thumb because it will blow your thumb off. Because the sound speed in water is what, 700 miles an hour? No, sound speed in air is 700 miles an hour. Sound speed in water is like 2,500 miles an hour. It's really large. It's really fast. But you can do it with air and a ping pong ball pretty easily. So, so it does. So like Jake said, it gets harder and harder to push because this gets smaller and smaller. So this gets smaller and smaller as the Mach number goes up, as the velocity, as the exit velocity goes up. Then you have this shrinking term here. So this gets even bigger as you get smaller. So there's so as the velocity goes up, the acceleration gets even larger up until the fact that it can't push anymore, and then it forms a shock. And once there's a shock, and the Mach number is 1, then you're stalled because d by dx is infinity or 0 or something. A shock happens, and stuff breaks. Jesse, do you go ahead? So once you get a shock, then things start to change. So in the same setup, as soon as I get past the speed of sound, then when the Mach number is bigger than 0, then d by dx of v, sorry, that is 0. So it will decelerate. If you have a converging flow and a converging nozzle and a supersonic flow, it will decelerate and stall and shock in that throw. So what you want to do is build a tube that gets just a little bit bigger so that then, on the outside, then when d by dx of the log of a is bigger than 0, so that it's getting bigger, then it will accelerate the flow. So you get it smaller to accelerate the flow until that doesn't work anymore, and then you get it bigger to accelerate the flow because now that's what's happening. So this is called a de Laval nozzle. Or a converging diverging nozzle. So it just looks like this. It gets smaller and then bigger. And the shape of the profile, you can get into the details about what shape it should have. There's papers on that. So here, in this part of the flow, d by dx of a is less than 0. And in this part of the flow, d by dx of a is bigger than 0. And here the velocity is less than 0, and here the velocity is bigger than less than 1, and here the velocity is bigger than 1, so it gets accelerated. So how to think about this? Think about it kind of like traffic. You've all been in traffic, right? You've all been in traffic when you're on the highway, and living here is really weird. I've always lived in bigger cities than this and spent a lot of time on the interstate that went through the big city, and I'm never on the interstate here anymore. I mean, except maybe if I'm going from Monroe to Thomasville. But if you're going down a Southern California 8-lane highway and one of the lanes is down, or any here, wherever, you're going down the highway and one of the lanes is blocked, what happens? You don't get faster. That would be pretty cool. That's what happens if it was water. But traffic is more like compressible hydrodynamics because the flow can compress. And the flow speed is dependent on the density in this complicated way. So supersonic flow is more like traffic. If I had a bunch of traffic coming into here, you can tell that it's going to slow down to a crawl until you get past that point, and then it'll expand again. And then after you get past the blockage, everybody gets to accelerate, right? Because your speed depends on who's in front of you. Yeah.
So this is also only work if the incoming fluid is subsonic?
Yeah, if you put a supersonic flow into this, it'll shock right here, and it will break.
So it's not like you would I guess, similar to like a linear accelerator, you could stack up
That's right.
There's a limit to
You
what-
can't, you have to do it in one shot. You have to do everything in this expansion valve. You can't put another expansion valve there either.
So you said in the lab you're in, they use Laval nozzles.
Yeah.
But they get to Mach 5.
Right.
So,
It just expands really far, and it's a
Okay.
huge object. So this object is this, the camera is about this large, and it's about this wide. And it's very cool. You can see just by the way they have the bolts, there's just a massive line of bolts where they bolted the bottom of the nozzle to it. But it's really just about making sure that your input flow is laminar as hell. So the input flow has to be really, really smooth, because if there's any turbulence, that turbulence will just rattle everything apart. So as long as the pressure is very high and the input flow is smooth, then you can accelerate it to pretty high Mach numbers.
so subsonic air is coming in,
Yeah,
and Mach 5 air is coming out.
yeah, that's right.
crazy.
That's pretty neat.
That's pretty
And they are stopped at Mach 5 because they can't get it any faster without heating the gas first, because it's coming out too cold. So if they wanted to go faster, then the air starts to liquefy, and then you don't have air anymore. That changes the dynamic entirely if you're liquefying half of the stuff that's coming out of your nozzle. All kinds of pressure. There's no way that's not getting turbulent. So that's the thing they're doing. Yeah.
Oh, sorry.
How thick is the area of the nozzle where it's pinched?
It depends on the nozzle. So for the project that I'm doing with Jonas, I think these objects are going to be about this big. So they're only less than an inch across. But for the big one, it's much larger. So they have like 2 cubic feet of good flow. So it depends on how you build it. Yeah.
So my next question was like, you said that like the air that comes out can be liquefied if it's like too fast. Why doesn't like the airspeed increase the overall kinetic energy of why doesn't like make the system hotter?
Because I should write that down. Because the temperature drops. So there's a huge pressure drop as you're expanding that nozzle. As it's expanding, if you work out what d by dx is doing minus d by d rho dx is doing minus dv dx. So the velocity is accelerating, the density is going down. So the way to think about this is I have a flow like this, and it's accelerating in this direction. The density is going down, and that density going down is pulling because it's making a pressure drop. The density goes down and the pressure goes down, which makes the density drop in that direction. So now you're getting pulled in that direction more by the density drop. Yeah.
So how would you use these to test like supersonic aircraft? Because if the pressure is going down so much and it's getting so cold, wouldn't that like affect the dynamics of what you're trying to test?
I mean, only if you have something that's temperature sensitive. So.
But it wouldn't care about the super low pressure or anything like that?
Only if you have something that's going to care about that. So,
Okay.
but if I make something out of aircraft titanium, it doesn't really care what the temperature and
Okay.
pressure is. But if I put something on the wall that is pressure sensitive, then I have to understand the pressure relationships.
Okay.
But yeah.
What, like, excluding the whole liquefying your fluid,
Uh-huh.
what would be like the limitations of this novel? Like how fast could you potentially make it?
What's the theoretical limit for a
Yes.
nozzle? I don't actually know, but they have a hard time above Mach 5. So Mach 5 is kind of, and a lot of it is practical engineering application issues. There are no aircraft that go that fast unless you're a rocket. So rockets can go that fast, but air-breathing aircraft can't, except for scramjets. And so a scramjet works basically on this same process. A scramjet, I think the fastest one they've made is like Mach 6 or 8. So that's pretty quick. Realistically, you run into the thermodynamics and the turbulence of making one go really, really fast. So I don't know if there's like, yeah, there's probably an actual limit, but I don't know. That's an interesting question.
Could you like make like a nozzle that's like not necessarily for supersonic speeds, but like just increasing the speed of the water? Like when you made this, like the first thing that came to mind was like a pressure washer.
Right.
And like how, like it's, the area increases right after the nozzle, and so we're working on the same principle that, like, you know, you're pushing water through a narrow thing, and then immediately as it comes out, it becomes faster, and that's why they use that.
Yeah, but so you have this term though is going to kill you. So unless you're faster than the speed of sound, then it's going to then
It's not gonna-
you don't have a minus sign. So these have opposite signs unless you're faster than the speed of sound, and then they have the same sign. So it could, but you'd have to have a supersonic pressure washer, and that would hurt.
What fraction of the speed of sound is the air coming in that gets it to Mach 5?
I don't know.
Okay.
Like, could you, in theory, like put it like 0.9 miles per hour, like right below it, or like
Yeah,
0.1?
it comes really down. So there's a nozzle that you design, and that has a certain V1 and a V2 that it's designed to handle. So there's a certain amount of acceleration that's expected, but I think that's just from the engineering design. So I could make one with a variety of input velocities. Okay. More questions on any of this stuff? I think that's all I got for the day. Yeah, homework due Monday. I'll have office hours on Monday. What time is, if I have office hours at like 3:30 on Monday? 3:30? You want an hour or so after that, 4:30?
Okay, because I have class at 3:30.
Okay, when, until when?
It's 4:45.
4:45. If I have office hours at 3? What, 2:30?
Yes.
Okay. Cool.
Thank you.
Yeah. So I'm gonna write down. Actually, on Monday. Yeah.
I saw like the Twitter post where someone asked like how fast you have to be on the moon to get it going to orbit, and apparently it was Mach 4.6.
Okay. Okay. Yeah, that's not too bad because I think it's.
The moon and going in orbit.
To be on the moon.
Yeah, no, to be on the moon and you're.
Oh.